हेलो हेलो एवरीवन। गुड मॉर्निंग। आप सबका स्वागत है मैथमेटिक्स की फर्स्ट क्लास में। यू ऑल आर वेलकम इन द फर्स्ट क्लास एंड द फर्स्ट चैप्टर ऑफ मैथमेटिक्स ऑफ क्लास 10th, which is the real numbers. So, are you people ready to read the real numbers? Okay, so let's start the real numbers. This is the chapter first of class 10th mathematics. To read this chapter, we need to have the strong concepts. We need to have the strong base of the rational numbers. So first of all, we all are going to read about the rational number to understand what does it mean by the rational number. So we all have studied the concept of the rational number in our previous classes too. So it is obvious that you all are familiar with the rational numbers. But still, for the sake of the convenience and for the sake of the revision, I am going to explain it again. Okay? So what is the rational numbers? Rational numbers are the numbers that can be written in the form of P by Q, where P and Q belongs to the integers and Q is unequal to 0. This is the definition of the rational number. I am going to explain it in Hindi also. कोई भी ऐसा नंबर जिसे हम p by q की फॉर्म में लिख सकते हैं, जहाँ पे p और q इंटीजर्स होते हैं और q की वैल्यू 0 के बराबर नहीं होती कभी भी, उस नंबर को हम रैशनल नंबर कह सकते हैं. दिस मीन्स दैट एनी नंबर which we can write in the form of p by q, where the p and q are the integers, belongs to integers, and the value of q is unequal to 0. Q should never be 0. Q must be never q must never be the 0, because if the value of q will become equal to the 0, the number will become the not defined, and thus the number does not exist in the collection of the rational number. Are you getting the point? If in the p by q the q becomes equal to 0, then it is not a rational number. It is a very necessary and essential condition. Okay? Now, second point is all the natural numbers and integers are the rational numbers, and all the rational numbers are all the integers. What do you think about it? Are all the rational numbers are integers? No, no, no. Now comes the irrational number. If we have studied the concept of the rational number, then the concept of irrational number arises by itself. So it is very important to study this concept also. We have studied that rational number is the number that can be written in the form of p by q, being q unequal to 0. Then what will be the irrational? Irrational will be just opposite of it. Okay? As its name is also suggesting in itself, the rational and irrational are opposite in themselves. Okay? So irrational number is basically the numbers which are not the rational are irrational. And irrational numbers are represented by the English capital letter T. Okay? Fine, moving ahead. Now comes real numbers. What is the real number? The collection of all the rational and the irrational number is called the real numbers. Suppose we have a bag, naming bag A, which contains all the rational number. Then we have the second bag named B. The bag B contains the irrational number. If we merge both bags A and B into the bag C, then it contains all the rational and the irrational number. Then we can say that bag C is the collection of the real numbers. Okay, now we can say that all the rational as well as all the irrational numbers are the real numbers. Fine, and it is also represented by the letter R. That was just the introduction and the prerequisite knowledge to study this chapter. Now, the first heading of the chapter begins. The first heading is the Euclid division lemma. Now we are going to read about the Euclid division lemma. First of all, I want to make you people understand what the lemma means to us. Actually, a lemma is derived from the Greek language. Lemma means a proven statement used for proving another statements. Okay, a lemma is a already proven statement. We can say that it is like an axiom. Okay, axiom, we are familiar with the term axioms which we used in our geometry sections in the class 9th. Lemma is just like an axiom. It is a proven statement that can be used and that is used to prove the other statements. So here is the Euclid division lemma. Euclid division lemma says that given positive integers a and b, there exist unique integers q and r satisfying a equal to the bq plus r, where r is less than b but greater than or equal to the 0. Actually, this is just the second form of the remainder theorem. It is related to the remainder theorem. If you people can correlate with that, whenever we divide, we have given the two integers a and b. Let's suppose that a is greater integer and b is the lesser integer, and if we divide the greater integer keeping it as a dividend and the lesser integer keeping it as a divisor, then we obtain some quotient and remainder. That quotient is represented here by the letter q and remainder is represented here by the r. And as we all know that remainder is either 0 or greater than it but less than the divisor, which is b here. So I think that Euclid division lemma is clear to you all people, and but still I am explaining it once again. That Euclid division lemma states that for any positive integers a and b, there exist integers q and r which satisfy the equation a equal to the bq plus r, where r is greater than or equal to 0 but less than b. Is it fine? And do you all understand it? Okay. This is a very important statement of this chapter, and you all should learn it for the examinations. And we are also going to use this statement in our questions and in the examples that are coming ahead in this chapter. Okay? Is it all fine? Is it getting inside your brains? Okay. Now, keeping this chapter in the very simple way and moving ahead, now we are going to solve the example 2. Let's see the example 2 of our book. The example 2 says that show that every positive integer is of the form 2q and that every positive odd integer is of the form 2q plus 1, where q is some integer. As we read this question, it seems that it is a very obvious statement and it is a true statement. But we now need to prove it. How can we prove it? We will prove it with the help of the Euclid division lemma. So let's see the solution of this problem. Here is the solution, that given positive integers a and b, there exist unique integers q and r satisfying a equal to the bq plus r is greater than and uh, equal to the 0 and less than b. This is the Euclid division lemma. So let here b equal to the 2, then a will become 2q plus r. If b equal to the 2, then the value of r can be the 0 or the 1. Now, the case 1 is when r is equal to the 0, then a will be equal to the 2q plus r, which is 2q plus 0, which is 2q. As a here is equal to the 2q, which is a multiple of 2, we can see that a is equal to the 2q. 2q means it is a multiple of 2, so it is even. Fine. Now case 2 is when r is equal to the 1, then a is equal to the 2q plus 1. As we can see that 2q was even, adding 1 in it will become, makes it odd. So here when r is equal to the 1 and a is equal to the 2q plus 1, it becomes odd. So we can say that, and it is proved, that any positive integer is of the form 2q, while any odd integer is of the form 2q plus 1. Now we will solve the second problem of this type based on the Euclid division lemma. This is the question from our exercise 1.1. It says that show that any positive odd integer is of the form 6q plus 1, 6q plus 3, 6q plus 5, where q is some integer. Now, trying to understand its solution, given any positive integer a and b, there exist unique integers q and r satisfying a equal to the bq plus r. R, where r is equal to or greater than 0 but less than b. This is our Euclid division lemma. Now we will let assume the value of b equal to the 6. Then possible values of r become 0, 1, 2, 3, 4, 5. There are 6 possible values of r. So case 1 is when r is equal to the 0, then a is equal to the 6q, which is even as it is a multiple of 2. Now second case is when r is equal to the 1, then a is equal to the 6q plus 1 equal to 2 multiplied 3q plus 1. As we can see, 2 multiplied 3q is the multiple of 2, and when we add 1 in it, it becomes odd. Third case, when r is equal to the 2, then a is equal to the 6q plus 2, which is even, which is all a multiple of 2. Then when r is equal to the 3, then a becomes 6q plus 3 equal to 6q plus 2 plus 1. The expression till the 6q plus 2 is even, as it is a multiple of 2, and when we add 1 in it, it becomes odd. So it is basically an odd. When r is equal to the 4, then a is equal to the 6q plus 4 equal to 2 multiplied 3q plus 2, which is even. Now, when r is equal to the 5, then a is equal to the 6q plus 5 equal to 6q plus 4 plus 1 equal to 2 multiplied 3q plus 2 plus 1. It means that 2 multiplied 3q plus 2 is an even, and when we add 1 in it, it becomes odd. So basically, looking at all these above statements, we can say that when a was equal to the 6q plus 1, it is odd. When a was equal to the 6q plus 3, it is odd. When a was equal to the 6q plus 5, it was odd. So basically, we have seen and we have proved that any positive odd integer is of the form 6q plus 1, 6q plus 3 and 6q plus 5. Is that clear to you all people? Now we will move ahead and we will solve the third problem of third problem based on the Euclid division lemma, which is a question from the exercise 1.1 NCERT textbook, question number 4. Here the question is, use Euclid division lemma to show that square of any positive integer is either of the form 3m or 3m plus 1 for some integer m. Now trying to understand its solution. First of all, we will write whenever we are going to do its solution, we need to first write the Euclid division lemma, which is, given positive integers a and b, there exist unique integers q and r satisfying a equal to the bq plus r, where r is equal to or greater than 0 but less than b. Now we will assume the value of b equal to the 3. Then r can take three values, either 0, 1 or 2. So the first case is when r is equal to the 0, then a is equal to the 3q plus 0 equal to 3q, and hence a square will become the square of 3q square equal to 9q square equal to 3 multiplied 3q square, which can be written in the form of 3m, where m is equal to the 3q square. Now the second case is when r is equal to the 1, then a is equal to the 3q plus 1. It becomes a square. When we try to calculate the a square, it becomes the square of 3q plus 1, which is 3q square. There are four problems in front of us, and the question is, use Euclid division algorithm to find the HCF, and we have provided the four sets of the questions. So first, trying to solve the first problem, 4052 and 12,576. Here we can see that we are dividing the larger number, which is the 12576 12,576, by the smaller number 4052. Then the quotient is 3 and remainder is 420. Now we will divide the previous divisor, which was 4052, by 420. It will give us the remainder 272 and remainder 148. Now we will divide 272 by 148. This process will be continue till we get the remainder 0. So continuing this process, now the remainder will be 24, was 135 and 225. First we will divide the 135. The next problem is tutorial is 867